Okay, let's look at number 3. Number 3 says a manufacturer wants to design an open box having a square base and a surface area of 108 inches. What dimensions will produce a box with a maximum volume? Okay, so let's look back at the important things that they've told us. They've said it's an open box, so that means we don't have a top, so that's going to impact our surface area. It has a square base, so that's going to be important. That helps us narrow down the variables that we need to use. Here's our constraint, the surface area of 108. Then we need to look at what they're asking. Maximum volume. So whenever we find the volume, that is what we're going to be taking the derivative of. So let's draw a picture to help us see what's going on. So we have a square, top and bottom. We have a height, something like that. It's not perfect, but you know what I mean. And there's our lines on the inside. That's really bad, but you know what I'm trying to draw. So our base is going to be a square, which means these two sides are going to be the same measurement. So let's call them both x. The other measurement we need, volume is always length times width times height. So we have length, we have width, and height. We'll just call it h. Make it easy on ourselves. So since volume is always length times width times height, when we look at our problem over here, our length is x, our width is x, and our height is h. So our volume is x times h, which will be x squared times h. This is what we are going to maximize. So that's what we're taking the derivative of eventually. But we can't yet because right now it still has two variables, x and h. That's where our constraint comes in. So it tells us about the surface area. Our surface area, we'll use S for surface area, means that we need the area of the bottom of this box and then each of the sides. So we need the area of the bottom, and then we're going to add the area of the sides, and we have 4 sides. We have 1, 2, 3, 4 sides. So the area of 4 sides. So let's talk about this in an equation. So S, the area of the bottom is one-dimensional, or two-dimensional, so it's x times x, which is x squared. Adding the area of the sides. So the area of sides are rectangles, so we still need base times height. The base of them will be x. The height of them is the height, h. And remember, we have 4, so we need 4xh. This is what is equal to the 108 they originally gave us. So this is 108 equals x squared plus 4xh. And remember, the constraint is what's going to help us narrow down our variables. So we need to solve this for something. The h is probably going to be the easiest to solve for, so that's what I would do. So we can have 4xh equals 108 minus x squared if we subtract that x squared over. Then divide both sides by 4x. And we get h, sorry about my computer, we get h equals 108 minus x squared over 4x. This is what we will use. So we will have an equation with all x's. So our new volume is x squared times 108 minus x squared all over 4x. You can take the derivative from here. You'd have to use the product rule, and then you'd have a quotient rule inside of that, which is fine. It would work out if you want to do that, but that could get a lot very complicated and there's a lot of places to mess up a sign or dividing or whatever. So let's simplify first. Simplifying this, you can distribute the x squared. So our volume would be 108 x squared minus x to the fourth. And then this 4x can split up under each of these. So we can have this over 4x and this over 4x. And these can simplify. 108 divided by 4 is 27. X squared divided by x is just x. And over here we have minus x to the fourth divided by x is x cubed. And then just over 4. This is much better to take the derivative of. So let's do that. Let's take the derivative. Because remember, we need to maximize this. And how we do that is by taking the derivative. So the derivative of v is 27 minus, remember, numbers are just numbers. They're not going to impact our derivative that much. So it's basically like multiplying by 4 out front, except for dividing by 4 on the bottom. So all we really need to look at is our variables. So we're going to bring the 3 down, and we will have x squared divided by 4. And there we go. This is what we set equal to 0 so that we can find the maximum, because we are trying to maximize the volume. 3x squared over 4. So we can add that 3x squared over 4 equals 27. We can multiply both sides by 4, and we'll get 3x squared equals 108. We divide by 3, x squared equals 36. And take the square root. We'll get a positive and a negative 6. But remember, this is in context. We cannot have a negative measurement. So really, all we care about is the positive 6. So our x dimension is 6. And we have units of inches. That means that if our width or length or whatever you want to call that side is 6, then the other one is also 6 inches. So we have 6 inches by 6 inches by, we need the height. So to figure out the height, we're going to use that 6 inches back into wherever we found our height. So we'll plug it into here. So our height will be 108 minus 6 squared divided by 4 times 6, which is 108 minus 36 over 24, which will give us 3. So our height is 3 inches. Try that again. Our height is 3 inches. And those are the dimensions that will produce a box with a maximum volume under these conditions.